Hello everyone. In the next lecture of thermodynamics, we are going to discuss the Carnot cycle and the Carnot theorem. In the last lecture, lecture number 20, we finished at this point efficiency. Efficiency is the ratio of work produced and heat supplied. Now we are going to find out this ratio in case of Carnot cycle for a machine which is working cyclically as shown in this picture. Here, this is the source, or this is the heat reservoir, which is giving out some heat, which is Q, and it has temperature T1 which is greater than that of a sink, where Q prime amount of heat is deposited and its temperature is T2, so that T1 is greater than T2, and in between this amount of heat, that means Q minus Q prime, is being converted into work, and the work produced is minus W. Now the ratio heat work produced and heat supplied, that means heat supplied is Q. This has some value, and let us find out this value in case of Carnot cycle. So here, when the temperature was T1, a system was having temperature T1 and it was connected to the source, and the system took some heat Q and it undergoes isothermal reversible expansion. So the system was preliminarily at state A, where the temperature was T1, pressure was P1 and volume was P1. Now it is undergoing isothermal reversible expansion. Definitely the system is having some ideal gases, and it's taking away some heat Q from the source, and since it is an isothermal expansion, its temperature still remains T1, but pressure has changed from P1 to P2. The pressure has decreased. In the PV diagram, we can see that the pressure of B is less than that of A, but the volume has increased, since in the x-axis it has moved towards the right hand side. So the pressure has decreased to P2 and the volume has increased to V2, but the temperature remains the same, T1. Now the system is now detached from the source and separately expanded again, but this expansion is taking place adiabatically. Okay, so that no heat is being transferred with the surrounding, or no heat is being exchanged with the surrounding. In that case, due to that expansion, it has to spend some energy, and due to that its temperature has fallen down, and that temperature is T2, and this temperature T2 is the temperature of the sink. Now the system would compress reversibly and isothermally. Due to that, it would release some heat, and that amount of heat is Q prime. So it is now connected to the sink, and the system is isothermally and reversibly compressed from C to D. In that case, its pressure, volume and temperature have all changed. Its pressure has increased from P3 to P4, volume has decreased from V3 to V4, but the temperature remains the same, T2, as it is connected to the sink, and since it is an isothermal compression. After detaching the system from sink, it has been separately compressed adiabatically, so that its temperature again increases to become equal to that of the source again. So this is a cyclic process, and in between some work is produced. So we have to find out the ratio of that work and this amount of heat which was extracted from the source. Okay, one thing I must say, that the difference Q and Q prime is should be equivalent to the work produced by the system or the machine. So a machine runs by following a Carnot cycle that involves 4 steps to complete the cycle, and during this course, minus W modulus amount of work is done by the system. And here AB is isothermal expansion, reversible expansion, BC is the adiabatic reversible expansion, CD isothermal reversible compression, and DA is adiabatic reversible compression to complete the cycle. And this is definitely a PV diagram. So let us calculate the overall work done here. This is for the 4 steps. So 4 W expressions to be summed up to find out the final work W. Okay, that means modulus minus W. So modulus minus W1 for A to B, it is isothermal reversible expansion. RT ln V2 by V1. Here the temperature T is T1, the volume V2 is V2, final volume, and the initial volume V1 was V1. So it is RT1 ln V2 by V1, and this is definitely equal to the heat absorbed by the system Q. But since this is isothermal expansion, there should be no change in internal energy. If this internal energy for step 1 is delta U1, then this value must be 0. Now for the step 2, the work done. The work done must be equal to the decrease in internal energy of the system, because here the change is adiabatic change and Q is 0. So according to the first law of thermodynamics, it is 0 equal to delta U minus W, or minus delta U equals to minus W, or modulus of minus W. So here modulus of minus W2 must be equal to minus delta U2. Now we know that delta U is Cv into T2 minus T1. So here instead of delta U we have put here Cv into T2 minus T1, and the negative sign as usual taking from here is taken from here. Okay. Now for the path CD, it is isothermal reversible compression. Okay. So it should be RT ln V2 by V1. Here V2 is V4 and V1 is V3, whereas T is T2. Okay, so that is why it is RT2 ln V4 by V3, and this amount must be equal to the heat released, and that is Q prime. Here, since it is an isothermal change, so the internal energy should be 0. So delta U3 for the step 3 is 0. And for step 4, adiabatic compression, adiabatic reversible compression, it is Q here again 0. So minus delta U must be equal to minus W, or minus delta U equal to, if we take modulus here, the value should be same. And since delta U is Cv into T2 minus here T1, here T2 is T1, and instead of T1 we have to write T2, because this is the final temperature and this is the initial temperature. I'm sorry, this is the final temperature and this is the initial temperature. So final minus initial. Okay, since the system, the temperature of the system is increasing from T2 to T1. Okay, and the negative sign is as usual taken from this negative sign. So it is minus Cv T1 minus T2. Okay, therefore the overall work done is modulus of minus W, that is the summation of the all work done of the all 4 steps, and these values are here given: RT1 ln V2 by V1, this one, and then this value minus Cv into T2 minus T1, so this is written, then RT2 ln V4 by V3, RT2 ln V4 by V3, and finally minus Cv T1 minus T2, minus Cv into T1 minus T2. So these two are same, the second term and the fourth term are same, so they are cancelled by each other. Only the first term and third term are left here, and this is equation number 1. So in equation number 1 we get modulus of minus W equal to RT1 ln V2 by V1 plus RT2 ln V4 by V3. Now here we see that this path BC, this is adiabatic reversible expansion, so this is adiabatic change. Here initial temperature was T1 and final temperature was T2. Initial volume was V2 and the final volume was V3. Okay, when you are taking the note, don't draw this diagram again, because for just make the lecture convenient I have reproduced here this picture, but you don't draw this here for the second time. Okay, when you are taking a note from the screenshot of the slides. Okay, so we can apply the rule for adiabatic rule. We know that Tv to the power gamma minus 1 equals to constant. So T1 V1 to the power gamma minus 1 must be equal to T2 V2 to the power gamma minus 1. Okay, here T1 is T1 but V1 is V2, and here T2 is T2 but V2 is V3. So it is T1 V2 to the power gamma minus 1 equals to T2 into V3 to the power gamma minus 1. Okay, now look at this path dA. This is also adiabatic change. Here initial temperature was T2 and final temperature was T1, while initial volume was V4 and final volume was V1. So here also it can be applied. so that T1 V1 to the power gamma minus 1 must be equal to T2 V4 to the power gamma minus 1. Okay, now if this equation 2 and 3 are divided, such as we are dividing equation 3 by equation 2, then easily we can get this relationship that V1 by V2 equals to V4 by V3, and this value can substitute the value of V4 by V3 in equation number 1. What was equation number 1? Here, V4 by V3. So here in place of V4 by V3 we can put here V1 by V2. So by doing this we can get this relationship, modulus of minus W must be equal to RT1 ln V2 by V1 plus RT2 ln V1 by V2. Okay, so this is V2 by V1 and this is V1 by V2. So in order to make them similar in similar order of the rational relationship, this is V2 by V1. So if we want to make this one also V2 by V1, so this sign should become negative. So we are doing so here, minus RT2 ln V2 by V1. Now we can take V2 by, ln V2 by V1 is common, R also common, then only T1 minus T2 is left. Okay, so the relationship is R into T1 minus T2 ln V2 by V1. So what is the efficiency value? Efficiency must be work produced divided by the heat absorbed, Q. Q amount of heat was initially absorbed, although all amount of Q was not utilized. Q prime was released to the surrounding, or here the sink, and Q minus Q prime was utilized. So the value of Q minus Q prime is actually minus W modulus, and this value is found to be R into T1 minus T2 into ln V2 by V2 by V1. Okay, and the value of Q is already determined here. Look here, the value of Q was what? RT1 ln V2 by V1, isn't it? So we are putting the value of Q here also, RT1 ln V2 by V1. So this ln V2 by V1 terms are cancelled by each other, the R are also cancelled by each other, only T1 minus T2 by T1 is left here. So the relationship of efficiency with respect to the initial and final temperature is eta equals to T1 minus T2 by T1. So thus we get this equation, which is equation number 4 here. Okay, but we know that eta, that means the efficiency, is also equal to Q minus Q prime over Q. Okay, so these two right hand side terms must be equal, so we can also write T1 by T2, T1 minus T2 by T1 must be equal to Q minus Q prime by Q, and by processing this equation we can reach to this relationship T2 by T1 equals to Q prime by Q, or Q by T1 equals to Q prime by T2. So here heat change by temperature is constant. Okay, this is a very important relationship, and this is actually the mathematical form of the second law of thermodynamics, and it has so many forms but all has the similar type of meaning. Likewise this one, heat change by temperature. So this is the mathematical form of second law of thermodynamics, where we find that this ratio is constant, heat change by temperature. Okay, and from this we can reach the conception of entropy, the mathematical form of entropy. Okay, now another small thing, that is the maximum efficiency. This is a very tricky thing. This one comes as a question in your exam, that in what conditions maximum efficiency can be calculated. Okay, so we have the expression of efficiency T1 minus T2 over T1. So in order to get the maximum value of eta, that means efficiency, either this one should be maximum or this one should be minimum. So in order to get this one to be maximum, T1 must be infinity, or the minimum value of T1, that means here the T2 must be minimum, T2 here. Okay, so if this one is infinity, okay, or this T2 is 0, then the maximum value of eta can be obtained. Okay, in both cases the result should be 1. So eta should be maximum, either T1 is maximum, as I have said, that is T1 is infinity, or T2 is minimum, that is T2 tends to be 0. Therefore the maximum value of efficiency is eta minus T2 by eta, that is equal to 1, or T1 minus 0 by T1 equals to 1. Okay, so this is the condition to get the maximum efficiency. That means the temperature of the source either should be infinite or that of the sink should be absolute zero. This is the physical significance. Now, Carnot theorem. This is the last part of this lecture. So from the second law of thermodynamics, two important theorems have been derived known as the Carnot theorem. Later we have to prove these theorems also. After a few lectures, after having discussed the entropy term, we must prove these two theorems. Okay, so let's see what are these theorems. So theorem number 1, a reversible engine is more efficient than a reversible engine. And number 2, all reversible engines are equally efficient working within the same temperature limits. So all the explanation and significance and proof of these two theorems would be discussed later on. Okay, so that's all for this 21st lecture of thermodynamics. Thank you. Have a nice day.